At its very core, radio is a mastery of the invisible. It is the art and science of wireless electromagnetism, the deliberate shaping of electromagnetic waves to carry information through the vacuum of space or the air we breathe. Before we could send a single signal, we first had to understand the fundamental forces at play. The story of radio begins not with an invention, but with a profound intellectual discovery. In the 1860s, the Scottish physicist James Clerk Maxwell, working from his study in Edinburgh, unified the disparate laws of electricity and magnetism into a single, elegant theory. His 4 equations predicted something extraordinary: that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. This self-perpetuating disturbance would travel through space as a wave, moving at a constant, calculable speed. When Maxwell calculated that speed, he found it was the speed of light. He had not only discovered the nature of light itself, but also predicted the existence of an entire spectrum of these electromagnetic waves, far beyond what the human eye could see. It was a theoretical triumph, but for 2 decades it remained just that, an idea on paper. The proof came between 1887 and 1888 in a darkened laboratory in Karlsruhe, Germany. Heinrich Hertz, a brilliant experimentalist, set out to verify Maxwell's theory. He constructed a transmitter, a simple circuit that, when charged with high voltage, would discharge a powerful spark across a small air gap. According to Maxwell, this sudden electrical disturbance should radiate waves. To detect them, Hertz built an equally simple receiver, a loop of wire with its own tiny gap. As the transmitter sparked, Hertz observed a minuscule, almost ghostly spark arcing across the receiver's gap, even from across the room. He had generated and detected Maxwell's invisible waves. He had proven their existence, measured their wavelength, and confirmed they traveled at the speed of light. Hertz, however, saw little practical use for his discovery, famously stating, "It's of no use whatsoever." He couldn't have been more wrong. Hertz's sparks were a fleeting phenomenon, difficult to observe. A more practical detector was needed. The breakthrough came from French physicist Edouard Branly, who in 1890 invented the coherer. It was a simple glass tube filled with loose metal filings. In their normal state, the filings had high electrical resistance. But when an electromagnetic wave, a radio wave, passed through them, the tiny voltage induced was enough to make the filings cling together, or cohere. Their resistance would plummet, allowing a current to flow in a connected circuit, which could ring a bell or make a mark on paper tape. The coherer was 1,000,000 times more sensitive than Hertz's loop, turning a faint, invisible wave into a tangible electrical signal. The next challenge was selectivity. Early transmitters broadcast on all frequencies at once, and receivers listened to everything. In 1894, British physicist Oliver Lodge demonstrated the principle of syntony, or tuning. By adding adjustable inductors, coils of wire, and capacitors to both the transmitter and receiver, he could make them resonate at a specific shared frequency. This allowed a receiver to pick out one station from a sea of noise. Meanwhile, in Russia, Alexander Popov adapted Branly's coherer into a practical device for detecting distant lightning storms. Each lightning bolt is a massive natural spark gap transmitter, and Popov's device, connected to an antenna, could log these radio emissions from hundreds of kilometers away. He had created the world's first radio-based meteorological instrument. It was the Italian inventor Guglielmo Marconi who synthesized these discoveries into a commercially viable system. Obsessed with long-distance communication, he systematically improved the transmitter's power and the antenna's design. His ambition culminated on December 12, 1901. From a powerful new transmitter at Poldhu, Cornwall, his team sent a simple message. Across the Atlantic, perched on Signal Hill in Newfoundland, Marconi himself listened intently on a coherer-based receiver, its antenna lofted by a kite in the gale-force winds. Through the static, he heard it. 3 faint, distinct clicks. The Morse code letter S. Skeptics had said it was impossible, that the curvature of the Earth would block the signal. But the signal had arrived, proving that radio could conquer global distances. The coherer was sensitive but clumsy and slow. A better detector was essential for receiving more complex information. In 1904, British engineer John Ambrose Fleming, a consultant for Marconi's company, provided the answer. He repurposed an effect discovered by Thomas Edison, creating the oscillation valve, now known as the vacuum diode. Inside a glass vacuum tube, a heated filament released a cloud of electrons. A nearby metal plate, the anode, could attract these electrons only when it had a positive charge. This created a one-way gate for current. When a weak alternating radio signal was applied, the diode allowed only the positive halves of the wave to pass, converting the alternating current into a pulsating direct current that was far easier to measure. It was a clean, reliable detector, paving the way for voice transmission. Until now, radio could only send the dots and dashes of Morse code by turning a signal on and off. The Canadian inventor Reginald Fessenden dreamed of sending voice and music. He pioneered a new technique, amplitude modulation, or AM. Instead of switching a carrier wave on and off, he used the sound waves from a microphone to continuously vary the carrier's strength, or amplitude. The information was encoded in the shape of the wave's envelope. On Christmas Eve, 1906, from his transmitter in Brant Rock, Massachusetts, Fessenden broadcast a short program of speech and music. Ship radio operators across the North Atlantic, expecting the usual Morse code, were stunned to hear a human voice, followed by Fessenden himself playing "O Holy Night" on the violin. The age of broadcasting had begun. Fessenden's broadcast was a landmark, but the signals were incredibly weak. The missing piece was amplification. In 1907, American inventor Lee DeForest provided it with his Audion, the first triode. He took Fleming's diode and inserted a third element, a delicate mesh of wire called the control grid, between the filament and the plate. A tiny voltage applied to this grid could control a much larger flow of electrons to the plate. A small change at the input produced a large, identical change at the output. For the first time, a weak radio signal could be made stronger. The Audion could act as a detector, an amplifier, and even an oscillator to generate the carrier waves themselves. It was the foundational device of the electronic age. No one understood the triode's potential better than Edwin Armstrong, a brilliant and tenacious engineer at Columbia University. In 1913, he discovered regeneration. By feeding a small amount of the amplified output signal back into the input, in phase, he created a positive feedback loop that multiplied the tube's gain thousands of times. A single Audion could now do the work of many. Then, in 1918, Armstrong invented his masterpiece, the superheterodyne receiver. The principle was ingenious. Instead of trying to amplify and tune the weak, high-frequency radio signal directly, he mixed it with a signal from a local oscillator inside the radio. This created a new, fixed intermediate frequency, or IF, typically 455 kHz. All the main amplification and filtering could now be done on this single, stable frequency. The result was a receiver with unparalleled sensitivity and selectivity, and its basic architecture is still used in most radios today. With sensitive receivers and the ability to transmit voice, the stage was set for mass media. On November 2, 1920, station KDKA in Pittsburgh, owned by Westinghouse, broadcast the returns of the Harding-Cox presidential election. It was a sensation. For the first time, hundreds of early adopters could hear history unfold in real time without waiting for the morning paper. The broadcast ignited a public craze. Radio transitioned from a hobby for specialists to a medium for the masses. Families gathered around ornate console radios, which became the new centerpiece of the living room. connecting them to a shared national culture of news, music, and entertainment. The airwaves quickly became a chaotic Wild West. Hundreds of stations sprang up, often broadcasting on the same frequencies, interfering with each other and drowning each other out. To prevent this electronic bedlam, governments stepped in. In the United States, the Radio Act of 1927 established the Federal Radio Commission, with the power to grant licenses, assign frequencies, and limit transmitter power. The act enshrined the principle that the radio spectrum was a public resource, not private property. This regulatory framework brought order to the crowded spectrum, while networks like NBC and CBS linked stations across the country, creating a unified national audience. While broadcast radio dominated the medium waves, another frontier was being explored. Marconi's transatlantic test had worked, but no one was sure why. The answer lay 50 to 600 kilometers above the Earth in the ionosphere, a series of layers of the atmosphere ionized by solar radiation. Scientists discovered that these charged layers could reflect high-frequency signals, shortwave radio, back to Earth like a mirror. A signal could be bounced one or more times, allowing low-power transmitters to achieve intercontinental range. This skywave propagation turned shortwave radio into the voice of international broadcasting and a global playground for amateur ham radio operators who could talk to the world from their homes. AM radio had a persistent problem: static. Lightning, electrical machinery, and other sources of interference created noise that was indistinguishable from the amplitude-modulated signal itself. Edwin Armstrong, never satisfied, sought a solution. After years of secret work, he unveiled a completely new system in 1933, frequency modulation, or FM. Instead of varying the carrier wave's amplitude, FM varies its frequency in proportion to the audio signal. The amplitude remains constant. This made the signal virtually immune to static and interference, which primarily affect amplitude. An FM receiver could simply ignore amplitude variations, resulting in a crystal-clear, high-fidelity sound that was impossible with AM. It was a superior technology, but its adoption was fiercely resisted by the established radio industry. The Second World War dramatically accelerated radio innovation. The need for reliable communication and detection spurred immense investment. Radio sonde balloons carried automated weather sensors and transmitters into the upper atmosphere, broadcasting back vital data for flight planning. Secure communication was paramount, leading to the development of encrypted field sets and sophisticated systems like SIG-SAILI for top-level voice scrambling. But the most transformative technology was radar, radio detection and ranging. By sending out short pulses of microwave energy and precisely timing their echoes, radar could locate enemy ships and aircraft at great distances, in darkness or fog. The invention of the cavity magnetron provided a source of powerful, high-frequency microwaves, making radar compact and effective enough to change the course of the war. After the war, the next great leap was miniaturization. For half a century, radio had been powered by fragile, power-hungry, and bulky vacuum tubes. In 1947, at Bell Labs, scientists John Bardeen, Walter Brattain, and William Shockley invented the transistor. This solid-state device could do everything a triode could, amplify and switch, but was tiny, rugged, and required very little power. The transistor revolution was swift and total. It untethered radio from the wall outlet and the living room console. By the late 1950s, pocket-sized transistor radios were ubiquitous, bringing music and news to the beach, the ballpark, and the automobile. Radio became a personal, portable companion. The ultimate high ground for radio is space. On July 10, 1962, NASA launched Telstar 1, the world's first active communications satellite. Orbiting high above the Atlantic, Telstar acted as a microwave repeater in the sky. It received television signals and telephone calls from a ground station, amplified them, and rebroadcast them to another station across the ocean. For the first time, live television could be exchanged between continents. Telstar was a low-orbit satellite, available for only brief periods as it passed overhead. It was soon followed by geostationary satellites, which orbit at an altitude of 22,236 miles, matching the Earth's rotation and appearing fixed in the sky, providing continuous coverage to vast footprints below. While satellites conquered global distances, a different radio architecture was needed to provide mobile communication to millions of people in dense urban areas. The solution, developed at Bell Labs in the 1970s and deployed in the 1980s, was the cellular system. This approach divides a service area into a grid of hexagonal cells, each served by a low-power transmitter. Frequencies can be reused in non-adjacent cells, dramatically increasing the system's capacity. As a user moves from one cell to another, the call is seamlessly handed off. This first generation, or 1G, of cellular was analog and offered only voice, but it established the fundamental principle that brought handheld mobile calling to the public. The digital revolution demanded that radio carry not just voice, but data. In the 1990s, new modulation schemes emerged to make this possible in the crowded, unlicensed frequency bands. Technologies like spread spectrum, originally developed for military security, and orthogonal frequency division multiplexing, or OFDM, proved highly effective. OFDM is particularly clever. It splits a single high-speed data stream into thousands of slower parallel streams, each transmitted on a separate, closely spaced subcarrier. This makes the signal extremely resilient to interference and fading. These techniques became the foundation for the wireless local area networks we know as Wi-Fi, and the short-range personal area networks of Bluetooth connecting our devices without cables. Today, radio is becoming increasingly intelligent and adaptable. The paradigm of software-defined radio, or SDR, replaces specialized hardware components like mixers and filters with flexible software running on powerful digital signal processors. A single piece of hardware can be reconfigured on the fly to become an FM radio, a GPS receiver, or a 5G modem. Modern systems like 5G use this flexibility to perform incredible feats. Phased array antennas with dozens of tiny elements can use constructive and destructive interference to form and steer narrow beams of energy directly at a user, a technique called beamforming. This increases efficiency and reduces interference. 5G can also use network slicing to create multiple virtual networks on top of a single physical infrastructure, each tailored with specific characteristics for different services, from ultra-reliable autonomous cars to massive IoT sensor grids. From Maxwell's equations on a page to Hertz's first sparks, from the vacuum tube to the transistor, from simple detectors to software-defined systems, the history of radio is a relentless story of human ingenuity. Each step built upon the last. Fundamental principles were discovered, clever devices were refined, and complex systems were organized to manage an invisible resource. What began as a laboratory curiosity has become the invisible architecture of modern life, a silent, pervasive force that connects, informs, and entertains us all. The conquest of the airwaves was not a single event, but a century and a half of brilliant steps into the unseen.